Thank you, Jack. So today I want to talk about generalizing perfect one factorizations from graphs to hypergraphs, more specifically K-uniform complete hypergraphs. Sorry, there we go. So a quick overview of what I want to talk about today. So we'll start off with some background. I'll introduce one factors and one factorizations of graphs, so we're all on the same page. And then I will show how they've been already generalized to hypergraphs. So before we do that, we'll define a hypergraph. So once again, we all have the same background. And then once they've defined one factorizations of hypergraphs, we'll take a step back to graphs and add on another special condition, which will make our one factorizations of graphs perfect. And we'll see that we can actually have three equivalent definitions when talking about graphs. And when we try to generalize each of those to hypergraphs, they no longer remain equivalent. So what we end up with is three different generalizations, namely connected one factorizations, perfect one factorizations, and Hamilton-Burge one factorizations of hypergraphs. So I'll go through each one of these, give some examples, and then wrapping it up, I'll show some known one factorizations and classify them in terms of C1Fs, P1Fs, or HP1Fs, before finally finishing with some still unanswered questions that we want to move towards. So what is a one factor and a one factorization of a graph? So a one factor of a graph is just a spanning one regular subgraph. And then if we can take a graph G and decompose the edge set of G into edge disjoint one factors, we call that decomposition a one factorization. So on the left here, I have a complete graph on 6 vertices, and I've colored the edges such that each color is a one factor. So this here is a one factorization. For example, we'll look at the red one. We can see it's one regular and it covers all the vertices. So it's a spanning subgraph. Sorry, bad time to have losing my voice. Anyway, so we can see that this is a one factorization of the complete graph on 6 vertices. So these have already been generalized before to hypergraphs. But just as a recap, what is a hypergraph? So a hypergraph is a generalization of a graph. So where edges of graphs are pairs of vertices, edges of hypergraphs are just subsets of vertices of any size. But we'll be talking about a specific type of hypergraph, which is called a K-uniform hypergraph. So K-uniform means that each edge of the hypergraph has precisely K vertices. And more specifically, again, we'll often be talking about a special type of K-uniform hypergraph called the complete K-uniform hypergraph on n vertices, which is the K-uniform hypergraph on n vertices whose edge set consists of all K subsets of vertices. So on the bottom of the screen, we can see an example of a 3-uniform hypergraph on 6 vertices. So on the left, I have it visually, and on the right, I've explicitly given our vertex set and our edge set. And we can see here that each edge contains exactly 3 vertices, so it's 3-uniform. However, it's not complete because it's missing the edge 1, 2, 4, for example. So we have our hypergraphs, and we can define one factorizations of hypergraphs in a similar way to graphs. So we'll say that one factor of a hypergraph is a spanning one regular subhypergraph, and a one factorization of the hypergraph is a partition of its edge set into disjoint one factors. So I've got the same example, same hypergraph from before, but now I'm coloring the edges in terms of which one factor they can belong to a one factorization. So here's the one factorization of that previous hypergraph with our 3 one factors. So a natural question will be, when do one factorizations of graphs exist? Well, there's an obvious necessary condition strictly speaking about K-uniform. So there's an obvious necessary condition in which K must divide n, because if K doesn't divide n, we can't even have a one factor because we can't cover all the points with a nice integer number of edges. So K must divide n in order to even possibly have a one factorization. And actually, it turns out that this obvious necessary condition is in fact sufficient, thanks to a theorem from Baranyai in 1974, which shows that for K greater than or equal to 3, we can have a one factorization of the complete K-uniform hypergraph on n vertices, if and only if K divides n. I also forgot to mention that the way we denote K-uniform hypergraph on n vertices is K, Kn. So I'll be saying that to save time. So now we have one factorizations of graphs and one factorization of hypergraphs. So we're going to step back to graphs and add an additional constraint in order to get what we call perfect one factorizations. So if we have a one factorization of a graph, we'll call it perfect if the union of each pair of one factors is a Hamilton cycle. So on the left here, I have a one factorization of the complete graph on 8 vertices. And on the right, I have every possible union of pairs of one factors. And if we just pick out a random pair, so this one I've circled, we can see here that it forms a Hamilton cycle. You can check yourself, but every pair will have this property, and we call this a perfect one factorization. So the reason I have K8 here as opposed to K6 is because once we get to K8, we have one factorizations that are perfect, but also one factorizations that aren't. So these one factorizations that are perfect are exceedingly rare, and we still don't know whether they're always possible to find a P1F. So P1Fs of graphs, or at least complete graphs, are a very well-studied problem. We have this famous conjecture that states for any n greater than 2, K2n admits a P1F. So K2n, that's just our obvious necessary condition for even a one factorization being able to exist. There are some known results I have on the slide. Due to time constraints, I won't go through them, but just to show that we do have some results about when these exist. So with that definition that I've given, we can also define P1Fs in 2 other equivalent ways. So we have a total of 3 equivalent definitions of P1Fs. I don't want to rule out that there aren't more, but these are the 3 we'll be talking about today. So we can ask that the union of each pair of distinct one factors is a connected subgraph, or the union of each pair of one factors is isomorphic to the same connected subgraph, or the union of each pair of distinct one factors is a Hamilton cycle. So if we take these 3 equivalent general definitions and try to generalize them to hypergraphs, they no longer remain equivalent. We can have ones that satisfy one, but not the other 2. So if we generalize the first definition, we get what we've been calling connected one factorizations, or C1Fs of hypergraphs. If we generalize the second, we have still been calling them P1Fs, or perfect one factorizations. And if we do the third one, we've been calling those Hamilton-Burge one factorizations, or HB1Fs. So now I want to go through and talk a little bit about each one, some of the results we've found, connections to other objects, just things of interest. So we'll start off with our C1Fs, or connected one factorizations of hypergraphs. So we say a one factorization of a hypergraph is a connected one factorization for a C1F if each pair of distinct one factors is connected. So on the bottom, we have that one factorization of our 3 uniform hypergraph we've been using throughout. And on the right, I've now represented our edges slightly differently. So here, each line represents an edge. The reason I'm using this visualization is it's much easier for us to quickly see that the union of each pair of one factors is connected. So this one factorization here is a C1F. So now that we know what C1Fs are, and we know that we're talking about complete K-uniform hypergraphs, what can we say about C1Fs of K, K, LK, where LK now is our n, because we know n has to be multiples of K. So what can we say about KKN, or C1Fs of KKN, sorry? So we've been able to show our first result, which is saying the unique factorization of K, K2K is a connected one factorization, is a C1F. So here I'm talking about complete K-uniform hypergraphs whose edge set consists of half the vertex set. Sorry, whose edges consist of half the vertex set. And you can quickly show that that one factorization is unique. If you want me to walk through it, I can do it after the talk or at GatherTown or anywhere. So then the next lemma, so we want to start, we start shrinking our edge size in the way we're searching. So our next lemma says that all one factorizations of K, K3K are C1Fs. So now the sizes of our edges are 1/3 of our vertex set. And we know no matter what one factorization we have, it will be a C1F. So it might start to seem that these could be quite boring. Maybe they exist all the time and they're not too interesting if they're always there. But it turns out for L greater than or equal to 4, we can always construct a C1F that is, sorry, we can always construct a one factorization that is not a C1F for the k, k, l, k. So once our edge sizes are a quarter or smaller of the vertex set, we can always construct one factorizations that aren't C1Fs. So then the interesting problem is, for what values of L do admit C1Fs? So in one of the other results we do have, we found an infinite family of one factorizations that are C1Fs. It comes from a construction of Chen and Liu that uses some group theoretic construction. And we're able to show that when, these are all for 3 uniform hypergraphs, sorry. So edge size 3. So we can show that when n is 2 to the p for some odd prime p plus 1, that we can construct C1Fs. So we have an infinite family, and that's all we can say right now about C1Fs of k, km. So now we'll move on to our second equivalent definition of P1Fs of graphs and try to generalize that and show some results. So now we'll be trying to generalize the idea of requiring pair of distinct one factors to be isomorphic to the same connected subgraph. So we generalize that as follows. We say a one factorization of our hypergraph is a P1F if the union of each pair of distinct one factors is isomorphic to the same connected subgraph. So similar to before's example, we have the same hypergraph we've been dealing with for our examples, but now I've just relabeled our vertices in order to quickly show that these pairs of one factors are in fact isomorphic as well as being connected. So this one factorization I've given is in fact a P1F. So now, as before, we want to start looking at what can we say about P1Fs of complete K-uniform hypergraphs. So before we can do that, I need to introduce the idea of repeated K-1 sets. So when I'm talking about repeated K-1 sets, I'm specifically talking about pairs of one factors having repeated K-1 sets. So we'll say a pair of one factors have a repeated K-1 set if there are K-1 vertices that appear in an edge of each factor. So here we have 2 factors of a possible 4 uniform hypergraph on 12 vertices. And we can see we have a repeated K-1 set or 3 set in the top left and a repeated K-1 set in the bottom right. So we have 2 repeated K-1 sets. So why are we talking about K-1 sets? Well, the goal that we want to prove is we want to try to show that for K greater than or equal to 3 and L greater than or equal to 2, we can have a P1F of K, K, LK if and only, sorry. So if there exists a P1F of K, K, LK, then K must equal 3. So P1Fs can only exist for 3 uniform hypergraphs. That's what we're trying to prove. And I'll give a quick sketch of the proof. So first off, suppose we have a one factorization of K, LK, which is a P1F. We want to then count the number of repeated K-1 sets of vertices that occur in every pair of one factors, and we'll call that A. And then we need to count the number of pairs of one factors in the one factorization, and we'll call that B. And because we've supposed that F is a P1F, we know that each pair of one factors must be isomorphic to each other, so each pair of one factors must have the same number of repeated K-1 sets. So it follows that A on B must be a positive integer. And then with some manipulation, we're able to show that A on B is not a positive integer for K greater than or equal to 4 and L greater than or equal to 2. So it follows that if we have a P1F of a K-uniform hypergraph, complete K-uniform hypergraph, then K must equal 3. Now, if anyone's interested, these are our values for A and B that we were able to count, if you want to double check or if you're playing along at home. So now our repeated K-1 sets are actually just repeated pairs because we have K equals 3. And also this integer A on B is really representing how many repeated pairs we have amongst each pair of one factor of the one factorization. So we know it's constant for a given P1F, but we don't know what we can say about P1Fs in general. So we have this really neat result that says that the pair overlap number, so how many repeated pairs there exist between every pair of one factors of our one factors of our P1F. So the pair overlap number of any P1F, regardless of our choice for n, is 2. However, the converse isn't true. If we have a one factorization of K3n with pair overlap number 2, it's not strictly a P1F, not necessarily a P1F, sorry. So now that we have this 2, regardless of our choice of n, it gives us this really neat connection between our P1Fs of K3n, and symmetric designs. So there's a symmetric design with these properties, but in the literature, these are referred to as biplanes of order n-2. So I have a construction. I don't have time to go through it here, but I'm more than happy to walk through the construction in GatherTown or anywhere else if you send me a message. So now that we've covered that, I want to just quickly show what are the known P1Fs we have. So the only known P1Fs we have are K33, K36, and K39. And in each instance, these P1Fs are unique. There's only one P1F of each hypergraph. So in the last couple minutes, I want to go through generalizing the idea that the union of each pair of distinct one factors forms a Hamilton cycle. And we've been calling those Hamilton-Burge one factorizations. So before we can generalize to Hamilton-Burge one factorizations, we need to cover what is a generalization of a cycle in a hypergraph. So when you generalize cycles to hypergraphs, you have like a couple different choices, but we've found that we get the most interesting results by choosing Burge cycle as our generalization of choice. So here we have a Burge cycle of a hypergraph, and a Burge cycle is just an alternating sequence of vertices and edges where the edge in the sequence contains the vertex that precedes it and the vertex that follows. So for example, E2 must contain the vertex V2 and V3, and EM here will contain VM and V1. And also, sorry, the vertices and edges in this sequence must be distinct. But there can be overlap between edges in the sequence, but they must be distinct edges though. So if the vertices of our sequence is our vertex set of our hypergraph, then we say it's a Hamilton-Burge cycle. So on the bottom, we have our same hypergraph we've been dealing with, and now I've highlighted a Burge Hamilton cycle, Hamilton-Burge cycle. So we go from 1 to 2 by the red edge, 2 to 3 by the yellow edge, 3 to 6 by the green, 6 to 5 purple, 4 to 5 blue, 5 to 1 cyan. And on the right, we have a different visualization of it just to help show how we're moving around the hypergraph. So we can note here that if we have a Burge cycle of n vertices, then we must need n edges. So that gives us some sort of count of how many edges we need for there to be enough edges for the union of one factors to have a Hamilton-Burge cycle. So we have to tweak our definition slightly then to make sure we always have enough edges. So we then say a one factorization of a K-uniform hypergraph is a Hamilton-Burge one factorization if the union of each K set of one factors has a Hamilton-Burge cycle. So now that we know that our K set of unions will have n vertices and n edges, we can start to think of our Hamilton-Burge cycle problem as a Hamilton problem in bipartite graphs when we look at our incidence graph. So here we can observe that a Hamilton-Burge cycle is in fact a Hamilton cycle of our incidence graph, assuming we have enough edges on the right, which we always will when we're looking at K sets of one factors. So using this property, we can use some results from Hamilton cycles in bipartite graphs to get some quick, easy lemmas about Hamilton-Burge one factorizations. So we can observe that a one factorization is a HB1F if and only if the incidence graph of the union of every K set of one factors has a Hamilton cycle. And then we have this theorem from Dang in 1989 that states if G's are connected spanning M onto regular subgraph of KMM, the complete bipartite on M vertices on each side, then G has a Hamilton cycle, which gives us as a corollary the unique one factorization of K, K2K is a HB1F. And then if we try to expand this to K, K3K, we can observe that the incidence graph of the union of K1 factors of a one factorization of K3K is a K-regular bipartite graph on exactly 6K vertices, which is a special edge condition of a famous conjecture from Hagfist in 1976, who conjectures that every two connected K-regular bipartite graph on at most 6K vertices is Hamiltonian. So this leads us to also conjecture that every complete K-uniform hypergraph on 3K vertices is a HB1F. And that's as far as we have for HB1Fs. So now I'll quickly cover some of our known one factorizations of K, K, and K. kn. So here are some one factorizations which were found to be at least a P1F, a C1F, or a HP1F. We've excluded one factorizations that were found to be non-interesting in terms of these conditions. So we can see here that we've got a couple different ones, not too much to note right now. But we do conjecture that these will be HP1Fs for this family of Chen-and-Liu symmetric infinites, but we don't have any proof of that yet. So now, just finally finishing with some open problems. So does K3n admit a P1F for all admissible values of n? We do know it's true when n equals 3, 6, 9. With that connection to biplanes, we can use some design theory rules to make the next one must be 18. That's the next feasible one. We can use the Bruchweiser-Chowler theorem to rule out some other values of n. So then also for C1Fs, we want to know if KLK admits a C1F for all L greater than or equal to 2 and for all K greater than or equal to 3. We know this is true for L equals 2 and 3, and trivially 1, I suppose. And for HP1Fs, we want to know if KLK admits a HP1F for all L greater than 2. And we know that for L only equals 2, and I guess 1 again, because that's trivial. And finally, we want to know that if our factorization is a C1F, is it also a HP1F? We're leaning towards yes, but we don't have a proof. So thanks for your time. Thanks for turning up. I look forward to any questions.
Okay, thank you, Jeremy. Can we quickly thank the speaker? And if you have any questions, raise your hand or put it in the chat. Otherwise, I can always start. We got one hand up from Jody.
Hey, Jeremy, thanks for your talk. So I have a question about P1Fs.
Yes.
On one of the slides,
sorry, graphs or hypergraphs?
And hypergraphs.
Yep.
In the slide earlier, you had like, these are the only known P1Fs.
Yes.
Why is it so hard to find them?
Well, that's a $1 million question. That's what we want to know.
Like, what are some challenges that you've encountered with like maybe techniques that work in graphs but don't necessarily translate across to the hypergraph space?
So I guess the way we found these in hypergraphs, well, this one is just a given. This one here is unique, so you're forced. And the third one, it's not actually constructed in like an intelligent way. It's small enough that we could just brute force construct it. So when we get to K318, it's much too large to do that. And we don't really have like a nice way, because a lot of the ways the infinite families of P1Fs are found, you can make like a generator and a starter and do some progression on that. And we don't know how to even phrase this one like that. But we haven't looked too hard. That hasn't been our primary focus, to see if we can figure out a way to generate this and then generalize that.
Cool, thanks.
Any other questions? I don't see anything in the chat or hands up, so I might ask one. So this is still on P1F, so maybe this slide would be appropriate, but it seems vaguely like perhaps like a similar kind of question to, do Kirkman triple systems exist for all admissible orders, which was an open problem for a long time. And eventually some kind of, they call like GDD type constructions were discovered for large enough designs. And then it was just a job of filling in all of the smaller ones. Do you have any like construction ideas for how you could use smaller constructions, join them together in some sort of way and get a bigger one?
No, I don't have any idea for that. There is a connection with Kirkman triple systems. You can use large sets of Kirkman triple systems to construct one factorizations. Yep. But so we have actually built one factorizations using large sets of Kirkman triple systems. They just weren't given here because they don't actually lead to any connected ones. Because the way they build it, I think often when you build with copies, you end up getting disconnected components. So that immediately rules out P1Fs.
Yeah, okay. So that's, I guess, the obvious problem with trying to use
Yeah, so,
constructions.
so I guess, yeah, when you start stitching things together, often like copies of versions, they stay quite disjoint.
Yeah.
So we
Yeah,
lose that P1F.
Yeah, that makes sense. The other question I had was more to do with Hamilton-Burge cycles. And I noticed that the vertex left out of each edge in the cycle, you know, starting from the red one, clockwise 3, 4, 2, 5, 1, 6. Is it a coincidence that that spans the vertex set, or?
Well, no, every vertex will appear 3 times. And in this cycle, they'll appear as a joint twice. So they have to appear once more as not a joint, and the only spot they can be is in a midpoint.
Okay, so not a coincidence here, but is it also not a coincidence for larger complete graphs?
Well, I guess, yeah, for any larger complete one, it'll now appear. So if we expand the size of our edge, it'll still have to appear k times.
Yeah.
So it's going to appear k minus, it's going to hit 2 times here as a link, and then k minus 2 times as a midpoint of an edge.
Right, okay.
Yeah.
Okay, cool. Any other questions?
I do have another question if no one else has any.
Yeah, go on, Jody.
But at the very start, you mentioned that in a normal graph, as in not a hypergraph, that these 3 conditions are all equivalent. I didn't really quite follow why they are equivalent. Do you mind elaborating on that a bit more?
So I guess the union of pairs of 1 factors. So we have a pair of 1 factors, we know it's going to be a cycle. So if we have a cycle that's connected, it's a Hamilton cycle. And all Hamilton cycles are isomorphic to all other cycles.
Right. But
So
in the hypergraph case, it might not be a Hamilton cycle.
Yeah, so in the hypergraph case, we can have it, well, we don't know. That's why it's one of our questions. We think if it's connected, it will be a Hamilton-Burge cycle, but we're not sure. So it's possible they are. Well, sorry, actually, the difference there is now with Hamilton-Burge cycles, we're talking about k sets of 1 factors.
Right.
So we can have a pair. We can have a 1 factorization like Beth, where each pair of 1 factors aren't necessarily connected.
Yeah.
But each 3 sets of 1 factors are connected, and then that gives them a Hamilton-Burge cycle. That's how they're different.
Yeah, okay. Cool.
And then for connected and perfect, it could just be connected, but it has a different pair overlap number in different pairs. So yeah, they can all be different.
Yeah, awesome. Thank you for answering my questions.
No problem.
Okay, I think that's about it in terms of time. Can we thank our speaker once more with our reactions?